start. Okay, so I'm just I have closed the light here. Does it look good? Okay, so if you want the light turn on, just let me know. I thought that will be, our screen will be better highlighted. Okay, so first of all, hello. Okay, great. It is working today. Okay, so first of all, we're gonna release the assignment for you guys to provide the project information. So as we mentioned at the very beginning, right, we need to do a cost project, and you can choose two types of projects: Kaggle or exploratory project, right? And we released the Kaggle competition invitation link to everyone last week. So you got 1 week to, you have already been able to use 1 week to experience that, go through that task, right? So and so everyone is requested to provide your project information by October 1st. I think you still have like 2 weeks to consider which project you're gonna do and what is the project team. Remember, only the exploratory project can have a team. Like you have at most a team of 2. No more than 2 students in one project. But if you're doing Kaggle, just doing a solo project, and also just to follow the requirement in the assignment and provide the confirmation if you're doing Kaggle, and which maps to your UID, or provide your team memberships and explain what kind of problems you want to address if you're doing exploratory project. This is the first thing, and please make a decision at your early convenience and start doing something. And the second thing is about homework 1, and it will be due next Friday. So if you have yet started right now, please bear with me. Let me repeat again. So I rarely see students can finish one homework in 1 day or 3 hours. That's really impossible. Right? So I'll suggest you to do it early, and I'm excited to say some discussions have already been conducted in campus. So please join in, and please do that and ask questions and leverage your office hours and etc. Okay. Any questions so far regarding the homework and projects? Okay, great. So let us wrap up our discussion about computational learning theory before we talk about the next machine learning models. So in the last lecture, we introduced several fundamental concepts in computational learning theory, like what is the definition of the generalization error, or in other words, the true error. Right? So the generalization error is defined as the probability for any instance drawn from the underlying data distribution. What's the probability your learned hypothesis makes a mistake? Right? So it's just the probability. This is a kind of like golden standard, but in practice, because we have no idea about the ground truth data distribution, right? Like you want to do image classification, you can collect a bunch of images from internet, from whatever places, right? But you don't know what is the data distribution that generates those images, right? It might be very complicated. It doesn't have any analytical form, right? So as the consequence, you actually don't know how to exactly compute the true error or generalization error, right? And then we instead to evaluate the so-called empirical error. Right? So empirical error is just the training error. When you train your model, right, finish the training, you just test your model on the training set and say how much, how well your learned model can fit the training set, right? So this is called the training error or empirical error, right? So one key topic in computational learning theory is to use training error to estimate, describe, or bound the generalization error. Because we don't know the generalization error, right? And and we'll see a few bounds as our semester goes through, and also see that some kind of bounds directly motivate those classical learning algorithms like support back machines. Okay, and then we talk about in a setting of computational learning theory, how would we view a classifier is good or a learning algorithm is good, right? So first we need to be clear that the training data are random. They are joined from some unknown data distribution. That means, okay, this collection of training set might be good, but at next time, the collection of training set might be bad, right? So that means that, okay, no matter how powerful your learning algorithm is, due to the influence on the training set, we cannot guarantee you 100% accuracy or 100% performance, right? So a realistic expectation for a good learner is that, okay, we expect our learning algorithm can have a high chance to learn a good hypothesis or classifier or whatever. And then we can define what is the chance is a high chance, right? And what is the level of the error, like less than 0.01 or less than 0.05, right? And chance could be 0.9 or 0.95. And based upon that, we define the so-called path learnability, right? So path learnability is essentially a criteria which differentiates those efficient learning algorithms. Meaning that, okay, if to achieve to learn a good hypothesis, meaning that with high chance, with a low generalization error, I only need a polynomial of many training examples. Then we will such kind of learning algorithm as good, right? So we can say this algorithm can learn this type of target functions. Otherwise, it's not, because you need a great many training examples which are usually feasible in practice, right? And you can add one more condition about computational cost, right? And you only need polynomially number of training examples to achieve such accuracy with high chance. At the same time, the cost for finding such hypothesis is also polynomial. Complexity is polynomial, right? So that is some algorithm we really seek for in practice, right? Otherwise, those algorithms only have a theoretical value if they're not practically useful. Okay, those are all like basic concepts. No requirement to do any kind of like mathematical improvement or derivation. Just to ensure that you understand those basic concepts, because we're going to use them everywhere. And also we want to use these concepts to explain certain machine learning phenomena. And next, we're going to use a little bit of mathematics under an ideal case to justify the so-called Occam's razor. Right? So we discussed, we introduced Occam's razor's principle when we talk about the decision tree learning. Right? We said that, okay, we believe that among all the possible trees which are equally well, which can equally well represent the whole training set, we believe the smallest tree will be the best, right? This actually comes from the Occam's razor, right? So in general, Occam's razor just the guidance, just the guidance for you to select models. Like for in any discipline, right? You have a set of observations or data, and you come out like 10 theories or 20 theories which can equally well explain the data. Then you got some kind of like requirement or need to select a model or rank those models or theories, right? And according to which should we rank those models? Right? Occam's razor tells us always select the simplest one. Right? The simplest one means that you have a simplest assumptions. You don't have extra assumptions. You have the simplest mathematical structures. You have a simplest modeling modeling components, etc. Right? So in other words, OpenTree says that okay, never put extra components without necessity. Without necessity, don't make your model more complex. Right? Don't add one more assumptions in your model, or don't add one more formulas or algorithmic procedure. Right? That's what OpenTree tells us. Right? So historically, this is just a widely prevalent idea across different schools of philosophy. Right? Meaning that you have many philosophies. Which philosophy you should believe. Right? But now it has already been extended to, nearly all kinds of scientific and engineering disciplines. Okay, so now we want to use an ideal case, a very simple case to justify the OpenTree. Right? So here we consider our learning algorithm. Of course, it's about machine learning. So of course, this is about machine learning, and we assume that we have a very powerful learning algorithm, which that based on the training examples. Say you have n training examples, you can always find a consistent hypothesis with zero training error, meaning that when you fit this algorithm, fit this learning model, m training examples, you can find a hypothesis or model which perfectly fits training data, meaning zero training error. Right? One example would be decision tree. And then the claim we made here is that okay, there exists a hypothesis, right, in our hypothesis space. Here, big H indicates the hypothesis space. This true error, the generalization error, is bigger than epsilon, but it's still consistent with m training examples. This chance is less than the size of hypothesis space H, big H, times 1 minus epsilon to the power of m. So basically it says, okay, remember we're running our powerful learning algorithm, right? And of course we want to find a consistent hypothesis which not only doing like zero training error, but also performs well in the future examples, right? So we want our true error to be as small as possible, right? Say at least less than epsilon. But this would be, the result would be, counter our expectation. Right? We might have found a hypothesis, although with zero training error, but does not perform well in the test stage, meaning that its true error or the generalization error is bigger than what we expect, which is epsilon. Right? So this thing actually means that okay, your learn hypothesis, although perfectly fit the training data, but it's bad. That means that okay, its true error is bigger than our expected level of epsilon. Right? We want this thing, the chance of this thing to happen. We want to quantify the chance of this thing to happen. Right? We claim that the chance of this to happen is less than this product, the size of H times 1 minus epsilon to the power of n. Okay. So here I want to emphasize that. Don't be confused here. So the randomness comes from the training examples. Right? So remember, you got a training set randomly drawn or randomly generated by some unknown data distribution. Right? So even your H, right, for any given H, we know the true error is a nature, right? Is a nature property of that hypothesis, right? It is bad, it is bad, it's deterministic. There's no randomness on a given hypothesis, right? But because of randomness of the trained data, right, even a bad hypothesis still has a chance to perfectly fit M examples, right? So that's why we can still view this as a random event. And now we want to show that the probability or the chance of this event is upper bounded by this. Okay? Any question regarding the understanding of this statement? Okay. Yeah, looks everyone feels comfortable. Okay, so now I want to use a few lines of narration to show this statement. It's pretty straightforward. It's just based on what you have reviewed and like in almost zero. Right? So first, let us first assume, okay, you have found such an h, and this h is given. And we know that h is a bad hypothesis, meaning that its true error is bigger than our expected level epsilon, right? So, as we mentioned, right, even h is bad, it does not mean it always predicts make wrong predictions over the examples drawn from data distribution. It still has a chance to give correct prediction, right? For one example drawn from the unknown data distribution, h makes a correct prediction. This chance is less than 1 minus epsilon. Why? Think about the definition of the true error, right?
Because h size is 1, that's why it's less than 1 minus epsilon. M would be 1 as well.
Yeah, if you apply this, yeah, it's straightforward. But right now, we want to prove this. Right? You don't need to, you cannot use this as your precondition. Right? Yeah. So now let us assume, okay, you have found, you know a specific h, which is bad. The true error is bigger than epsilon. Now, I claim that the very first observation is that, okay, given any training example, one training example, h is still consistent with this example. This chance is less than 1 minus epsilon.
Right, so if epsilon is the chance that it's bad, 1 minus epsilon is the chance that it's randomly right.
Yes, exactly, right? Remember, the definition of the true error, right? Or the generalization error is just the probability that you make wrong prediction, right? For any example drawn from the underlying data distribution, right? So the probability that you make an incorrect prediction is bigger than epsilon, then the probability you make correct prediction is less than 1 minus epsilon, right? It's just according to the definition, very straightforward conclusion, right? So if we get our first observation, h is bad, yeah, consistent with one training example. This chance is less than 1 minus epsilon, right? And now suppose we have an m training example, right? And we assume that all those training examples are drawn IID from the data distribution, meaning that they're independently, identically distributed according to the data distribution, right? So what's the chance that h is consistent with all the m training examples? For one example, your chance is 1 minus epsilon, right? Remember, different examples are independent. So the chance h makes a correct prediction with another example will be upper bounded by 1 minus epsilon again, right? So now for m examples, you just multiply the response together. You end up with the upper bound for that hypothesis which are consistent with all m training examples, right? Which is 1 minus epsilon to the power of m. Okay? Does it sound good? Very well. Okay. So now we get our second result, which is also pretty straightforward. H is bad, but consistent with all m training examples. This probability is upper bounded by 1 minus epsilon to the power of f. Right? But we have finished, right? Finished the proof, because our claim here is not talking about a particular hypothesis. It's talking about the hypothesis space. Our claim here meaning that, okay, there exists a hypothesis in this whole space such that it's true error bigger than epsilon, and but consistent with all the training set. The probability is upper bounded by this, right? We need to show this, right? But how can we move? How can we extend these results to from a single hypothesis to a hypothesis space? So what's the probability that there exists some bad hypothesis in H? Yeah, consistent with all the training examples. The idea is just, exactly what we have reviewed in homework 0. So we can define this thing as an event, right? This actually represents the event part here, right? The event A is defined as there exists some bad hypothesis in our hypothesis space, which is consistent with the training set. Meaning that, okay, we know there's some kind of event happened that across this hypothesis space, one hypothesis is bad. There exists one hypothesis bad. We don't know which particular hypothesis is, right? We just know, okay, there exists one hypothesis in this whole hypothesis space, which is bad, meaning true error is bigger than epsilon, but it can correctly predict all the training examples. Right? So we just want to bound the probability of the occurrence of event A. Right? How can we do that? Right? Remember, we can view event as we can composite events according to sub-events or more anthem events, right? By using set operations, unions or intersections, right? So actually, this event A can be represented by a union of a bunch of more anthem events, right? That would be, okay, A can be represented by, okay, the very first hypothesis is bad, yeah, consistent with all M training examples, or the second hypothesis is bad, yeah, consistent with all M training examples, or blah blah blah, or the last hypothesis in this big H is bad, yeah, consistent with all training examples. It's just the decomposition of this event. We know that, okay, this big event can be represented by a union of those individual events. Right? And now we make the connection between the event or the probability for a whole space, meaning a whole set, and the event for each particular element or hypothesis in this hypothesis space, right? So now we can, to be succinct, right? We can represent A by the union of B1, B2, B3 up to B big H. Big H index is the last hypothesis in hypothesis space, right? And each B1 represent this single event. B2 represent this single event. So we know that the probability of an event A, right? The union of set events can be upper bounded by the summation of the probability of each individual events, right? Remember, this is our one problem in our homework 0, right? And we give a hint that you should use induction to show that. Of course, you can use like full version if you want to extend this. The probability is very long formula. Probably you can also be able to show this, but it's not trivial, right? Using induction will be the easiest approach, right? So now we know that P of A is upper bounded by P of B1 plus P of B2 up to P of B big H, right? And each of these single events, right, their probability is upper bounded by 1 minus epsilon to the power of F. Why? Because this single event is talking about the event happened on this particular or specific hypothesis, right? So you just add all those bonds together, right? You have a size H event, right? You add them together, you've got the upper bound, which is size of H times 1 minus epsilon to the power of F. And that's it. Any questions so far?
Sorry, why did you put big H on union? The part of big H?
Union here?
No, PBH.
Oh, this is just the index, right? So suppose you have a 10 hypotheses, your hypothesis space, right? You're going to index those hypotheses from B1, B2, B3 to B10. The big H just is the size of it's just the size of hypothesis space. Any other question? All right. So now we are able to show this claim, right? So the probability that there is a hypothesis across the whole hypothesis space that this hypothesis does not perform very well in general, but still consistent with M-training examples, this probability is less than size of hypothesis space multiplied with minus epsilon to the power of n. Right? So of course, we don't want these things to happen. Right? We don't want an learning algorithm which can find hypotheses which give zero training error, correctly predicting all the M-training examples, yet has bad true error, right? Bad generalization error. How can we avoid this? And a strategy to reduce this chance. Any intuition? I mean, just the intuition. No need to do some mathematical things right now. How can we reduce the chance that, okay, we got a consistent learner yet performing badly in the future?
Don't make it match all M examples.
Make what?
If it never perfectly fits the M set, then it'll never have this probability.
Oh, that's a one strategy that you don't want your learning algorithm to be consistent, right? To be so powerful. Yeah, that's definitely one strategy. But let it just stick to the assumption that, okay, you're gonna always have such a powerful algorithm.
Increase M.
Yes, exactly right. So if you can increase M intuitively, right, the more training examples incorporated, right, the more examples your learned hypothesis fit more training examples, the less chance it performs badly, right? So then, how can we make it clear, right, based upon the result we get here, right? So let's assume that we want this probability to be small. That's some tolerance level, delta, right? Delta you can take to be 0.1, 0.05, whatever. Right? And we know that this probability is upper bound by this. So as long as we can make this upper bound less than our designated level, right, we can reduce the chance of this thing to happen to be less than our expected level, right? So now, what we need to do is just to solve this inequality. You solve this inequality to ensure that the upper bound of this probability to be less than our designated level in terms of M, right? The training example, the size of training data. Right? And from that, we can say, okay, if M is bigger than something, and we can ensure that, okay, the probability or if M is bigger than something or M is large enough, we can ensure that the chance our learned hypothesis is bigger than epsilon is smaller than some designated tolerance level. Then the remaining thing is how to solve that, right? So we can take logarithm on both sides, right? It doesn't change the direction of the inequality. And then, I mean, to be easier, I mean, you can solve this directly, but here to be more interpretable, to be more transparent, we want to review some kind of structures inside the results. So we're going to further leverage an inequality, which comes from the Taylor extension of this e to the power minus x, from which we can obtain that logarithm 1 minus epsilon is less than minus epsilon. So we substitute minus epsilon for logarithm 1 minus epsilon into left hand side, right? You got an even lower bound, right? So actually, you got this, right? You got logarithm size of h plus m, logarithm 1 minus epsilon less than logarithm size of plus h and 1 minus epsilon, right? Sorry, it's upper bound for this, right? As long as we can make this upper bound less than logarithm delta, we can ensure this one is less than delta, and we know that the probability of that the true probability of that even to happen is less than 1 minus logarithm delta, right? And then you just solve it, and just arrange the terms, which is just simple math, and then you can get a lower bound of the number of training examples. In other words, we can claim that if m, the number of training examples, is bigger than this thing, then the probability to find a hypothesis which is bad, yet consistent with m training examples, is less than the designated level delta. Okay? Any questions so far?
How do we know epsilon?
What?
How do we know epsilon?
Epsilon is some kind of like a designated level. Like for example, I believe a bad hypothesis will have true error bigger than 0.1. Right? But for other problems, you might view epsilon to be 0.2,
Okay.
which can be viewed as a appropriate bad hypothesis.
So for the size of the hypothesis space, so is there any upper bound or like is it finite? So how do we know that?
Oh yeah, that's a very good question. Actually, here we definitely will assume the size of hypothesis is finite. But of course, I mean, as I just mentioned before, this is a very ideal case because we'll see later the size of hypothesis is often infinite. So for infinite case, we're gonna have we need some other bounds of the number of training examples to show the same kind of guarantees. But we'll talk about it later.
So epsilon is something you give out arbitrarily.
Yes.
Okay.
Yes, it really depends on the users and depends on the problems. And here also delta is something you're given. You give, and you want that the chance you find good hypothesis, you find a bad hypothesis to be less than this level, you feel good, right? Of course, you cannot set delta to be 0. There's no guarantee delta to be 0, but delta can be quite small. Let's say, as long as run this training algorithm, I got 10% chance to get the bad hypothesis, despite the bad hypothesis gives 0 training error. If you view this as bad, then I can set delta to be 0.1, right? But someone may say, okay, this is too risky, right? I want to set delta to be 0.01, meaning that okay, only have 0.01 chance to get bad hypothesis who are seemingly well, right? Perfect fit all the training examples. Okay, so we can restate the results in another way, right? Meaning that if m is bigger than this thing, then we can find a hypothesis with probability at least 1 minus delta. The h, the learned hypothesis h is consistent with all m training examples will have true error or generalization error less than epsilon. This is just the same results in the opposite way, right? In this here, we're just saying, okay, if m is bigger than this, then we'll say, okay, this happened, meaning that your true error is bigger than epsilon, this chance is smaller than delta, right? And it's equivalent to say, okay, the true error is less than epsilon, this chance is bigger than 1 minus delta. The same thing, right? So now let us say, let us look into the statement here. Right? This statement actually tells us to find a good hypothesis with high chance. Of course, the goodness level and the chance level are given or provided by delta and epsilon. Right? Now, how many training examples do we need at least? So we can take a look at the structure of this lower bound. This is called sample complexity bound. Right? So, and we see how different choices of the error level and the chance level will lead to different sample complexity bound. Okay? From which we can say how does the number of training examples should vary accordingly. So first we can see that if you want even smaller error, meaning that you want more accurate, like a learned hypothesis, with the same high chance, right? How does the sample complexity vary? Right? If you decrease epsilon, right? How does the sample complexity bound vary? How does the right-hand side vary if you decrease epsilon?
That's going to be bigger, right?
Yeah, that's going to be bigger, right? Epsilon is smaller, and then 1 over epsilon is bigger. And the right-hand side, which is the sample complexity bound, the lower bound of number of training examples, will grow, right? So this is reasonable. Why? Because intuitively, the more accurate you got your learned hypothesis, the more training examples you will need, right? Any question? Okay, so let us look at the term in the middle, right? Here's the logarithm of size of h. So what does that mean? Suppose our error level and chance level are all fixed, right? Both fixed, epsilon and delta are fixed, right? The larger the hypothesis, the larger the lower bound, right? Meaning that the more training examples you will need to achieve the same true error with the same chance. Right? What does that mean? Means that, okay, if we're going to search over larger hypothesis space to achieve the same performance, you have to provide more training examples, right? This actually reflects Occam's razor principle. Right? So remember, Occam's razor principle meaning that, okay, I want to select simpler models, right? What does simpler models mean, right? What does a simpler model means? One perspective would be, okay, the smaller hypothesis space. Maybe I just search over, say, 2-level decision trees, right? Rather than search over 10-level decision trees. The former, the hypothesis space, will be much smaller than the latter, right? And given the same epsilon delta, the former will require a much smaller number of training examples, right? I mean, to achieve the same error level under the same high chance, right? And the last term, 1 minus epsilon. Oops. I'm sorry. Yes. My pointer is out of battery. Okay. So the third term is about the chance level or the confidence level, right? So we can see that the smaller delta, the larger the bound, right? Because 1 over delta, right? So the smaller delta means that the higher the chance. Like if you reduce delta from 0.1 to 0.01, meaning that you increase the chance to get a good hypothesis from 0.9 to 0.99, right? You largely improve. If you want to increase the chance that you get good hypothesis, you have to increase the number of training examples as well, right? So you can see that although from a very kind of like straightforward mathematical derivations, we end up with a very good indicative structures showing how the samples are determined by, the number of training examples are determined by our expected error level, our confidence level, and also the complexity of your learning model, right? And later we'll say, we'll use kind of similar strategy to analyze algorithms and motivate development algorithms. So, and in midterm, I think this is something I want to emphasize again. Right? This reflects Occam's razor in terms of the sample complexity. In other words, even from the perspective of the number of training examples required,
I'm kind of having a hard time understanding this relationship between the error and the hypothesis, the size of the hypothesis space. It seems like they should be connected in some way. I mean, you should be able to expect low error with a small hypothesis space, in my mind. But this equation doesn't want to have them connected that way.
oh, that's a very good point. Here we're assuming, okay, no matter how large or how small hypothesis you have, you always return a hypothesis with a zero training error. This is indeed a very strong assumption.
Okay.
Yeah, but what you're saying is right.
Okay.
It's possible that, okay, if you reduce, I mean, in practice, if you use a smaller hypothesis space, you cannot give zero training error. But here, let's just assume, okay, your learning algorithm is so powerful, and the hypothesis spaces you're looking at are all big enough, such that, okay, for any training examples with size M, they all contain one hypothesis which gives zero training error. And under that case, we can compare different number of training examples required for different hypotheses. But later, we'll definitely provide extra bounds which account for the training error itself. Any other question? Okay, so let me stress again, right? So this simple result, again, is from a very ideal case, right? Shows that Occam's razor's principle, right, justifies Occam's razor's principle in the advantage of number of training examples, right? To achieve the same training error under the same chance, right? The simpler the hypothesis space, the smaller hypothesis space will be better because it requires less training examples, right? So now it leads to, the question, right? Someone asked just a minute ago, right? Here we assume the hypothesis space is finite, right? But what if your hypothesis space is infinite? Of course, this sample complexity is not meaningful at all. Right? This lower bound will be infinite. Right? And then how can we derive a sample complexity bound? Right? And we'll talk about it later. Right? And actually, when we talk about support vector machines, we'll introduce the concept which can, even for infinite hypothesis space, we can give a appropriate measure of the complexity of this hypothesis space. Okay. Okay. So we have finished the brief introduction about the computational learning theory, and hopefully you're not sick of it. These are just providing some basic concepts and some kind of idea, and which we're going to talk about again and again. And when we proceed to different machine learning models, their motivations, their development, and so on. Okay, so now we're going to jump to the next machine learning method, which is called ensemble learning. This is very important, very commonly used machine learning strategies. As the name suggests, ensemble learning means that, okay, I'm gonna use a set of base learners. Right? We're gonna assemble them into a more powerful learner. That's why it's called ensemble learning. So the most popular ensemble learning strategies include boosting and bagging. Right? So that's our focus for this topic. Right? We're gonna first introduce the idea of the boosting, and then we're gonna discuss the most popular and successful boosting algorithm, which is called EDA boost. And everyone will be requested to implement your own EDA boost version, and then test it on real-world data sets. And then we'll move to the bagging methods, and we'll see that bagging methods is even simpler. Or even simpler than boosting, but bagging can perform as well. Can perform very good as well. But we will give some theoretical analysis and justify why bagging, which is a so simple strategy, can give a better generalization performance. Okay. So first word is boosting. So the boosting is a general learning approach to construct a strong learner given a collection of weak learners. In theory, these weak learners can be possibly infinite. Of course, in practice, that won't be possible, right? You cannot run your learning algorithm forever and ever. You have to choose a finite number of base learners. So historically, the boosting algorithm was motivated by a theoretical question. Like this is a seminal work made by Robert Spear. He was the professor of Princeton for many years now in Microsoft research. So, so he wants to answer some kind of theoretical question, which we're going to discuss later. Right? So, here I just want to emphasize that it is practically very useful because it is a way to create a strong learner using only weak learners. Right? You don't need to first to create a strong learners. Right? You just create a very simple, stupid learner. Just create a set of them, and then boosting is just a smart way to combine them and end up with a very much more powerful one. And of course, it's a type of ensemble method, and in general, ensemble method is a class of learning algorithm that composes classifiers using other classifiers as building blocks. And boosting has a stronger theoretical guarantees. So, how practically, what are the successful applications of boosting? Right? So, a very prominent example will be the face detector. So, nowadays, like if you use your digital camera or even use your iPhone to take pictures, and you often see that okay, it can automatically detect the faces, right? And they show some like green bounding boxes of those faces, and just to remind you to adjust the angle and take a good frame, right, to take a picture. Right? So those algorithms are typically implemented by the so-called EDA boost, which we're going to discuss, which we're going to focus in this topic. Right? And other successful applications include handwritten letter recognition, right? Text classification, use tagging, information retrieval, DNA sequence analysis, etc. So the formulation of boosting is as follows, right? And of course, you're not required to really do some theory based on those definitions, but it's just to give you an idea, to give you a formal definition. Right? So the parallelability we just discussed before, we call them strong pack algorithms because this algorithm can for any data distribution, for any error level and the confidence level, we only need a polynomial number, many random examples to find these quantities with true error less than epsilon with high chance, which is bigger than or equal to 1 minus delta, right? So this is if an algorithm can satisfy this, we call this a strong pack algorithm, right? It is not only sample efficient, but also can give you very good performance, right? And of course, the requirement of such algorithm is too high, right? The bar is too high. So in practice, we might end up with many much weaker algorithms. Meaning that okay, it's still sample efficient. Meaning that okay, we still need polynomially many random examples, but we cannot guarantee that high accuracy. We can only guarantee your true error is bigger than some lower bound, which is half minus gamma. So gamma is really very small, meaning that the performance is only slightly better than random classifier. Right? So if you take epsilon to be 0.01, right, it means that okay, your train classifier is accuracy is just as bigger than 0. Its error is just smaller than 0.49, right? It's quite bad, right? But just slightly better than you just throw a coin to decide if it's positive or negative. So we call this kind of algorithm as weak path algorithm. Path just means okay, you just need a polynomial number of training examples, right? Meaning that in practice it is still efficient. You don't need to run whatever and ever get to the result. So then the question is that okay, this is the theoretical question. Question is that okay, if we know that some type of target functions or concept can be learned by some weak path algorithm, meaning that some weak learners and learners, of course, the learning performance won't be good. The accuracy is just slightly better than random guess. Is there a stronger algorithm, strong path algorithm can learn this concept? That's the theoretical question, which motivates the development of boosting algorithm. Does it make sense? And no need to memorize this. And I won't put any example on this, just to give you some kind of formal definition of this and how this is motivated. Okay?
With this clarify, if the big learner still needs to know, would you answer the question? Yeah.
I wouldn't answer this question in theoretical perspective, but I'll give you some algorithm, and practically to demonstrate. I will demonstrate those weak learners can be assembled into a strong algorithm. Any other question? Okay, great. So here is just a quick history of the boosting algorithm development and the origination. I mean, the standard work is from Robert Shapir's paper in 1989. Right? It provided the first provable boosting algorithm, but the practical performance is very bad. And then later, Froome, in 1990, he proposed the optimal algorithm that boosts by majority, and then they do some experiments using boosting, and still have some practical drawbacks. But the breakthrough was made in 1995, and they introduced the so-called ADA boosting algorithm, which is our focus later, and it shows very, very strong practical advantages over other boosting algorithms. They actually perform very well in many applications. And then after the boost, there are many follow-ups, a huge number of papers and practical applications. And there's two pioneers, Froome and Robert Shapir. They won the Nobel Prize in 2003, which is the top prize in computational learning theory. So now, I want to introduce. Now we want to focus on the ADA boosting algorithm. So, but I believe this kind of like a high-level idea have already been captured by everyone, right? So, I want to use a toy example first to show how ADA boosting is working. So, suppose these are our training examples. Those positive and negative examples in the plane. And we have a set of weak classifiers. Our weak classifiers are just axis parallel lines, right? You either find a x-axis, horizontal line, partition those data set, or you find a vertical line, partition this data set. So the ADA boost procedure is just iteratively generate a series of weak classifiers, either horizontal or verticals, and at the same time, reweight those training examples. We're going to update the weights of training examples according to the performance of the weak classifiers in the last iteration. So at the beginning, we're going to view all the examples are are equally important, meaning that the weight for each example is just 1 over the total number of training examples. So then we just run our weak learner on this set, right? And it ends up we find our best learner, which is H1, right? The best classifier on this data set, because it's a weak classifier, so it doesn't guarantee 100% training accuracy. Right? You still end up with 3 mistakes, right? So these 3 positive examples are mistakenly classified as negative by our H1. And we can calculate error, which is 0.3.
Shouldn't that error be 3 over 8 because those 2 are classified already?
Well, actually, we calculate error over the entire training set. It's just the imperial error, the whole training error. So you have 10 training examples, right? And you use your learn hypothesis to predict all the 10 training examples. You end up with 3 mistakes. So your error is epsilon 1, 0.3, right? So now we'll proceed to the next round, right? And the very first step in the next round will be, okay, I'm gonna increase the importance of this mistakenly classified examples, and then downweight the remaining examples which have already been correctly classified by H1. Why would we like to do that? We want to highlight the importance for those misclassified examples, right? So that in our next round, our new weak classifier can correctly predict those examples, right? Meanwhile, because the remaining examples, like those ones they have already been correctly classified by the previous classifier, so they are not that important to the new classifier. So we're kind of downweight them. So this figure illustrates how the sample weights vary after the updates, right? So we can see that we amplify the importance of those mistakenly classified examples by H1, right? And then downweight the importance of the remaining examples. So in general, we use dt to denote the set of weights at round t, right? At iteration t, right? 1 for each example, and those weights indicate how much should the new learner care about this example in the training procedure. And here we put an important constraint that the summation of all the weights must be 1. So at the beginning, of course, all the examples are equally important, and so their weights will be 1 over m. Right? Suppose we have m training examples in total. But when the training procedure proceeds, right, you can see that the distribution of those weights kind of vary, right, according to the classification results made by the weak learners in each iteration. So now we get our updated weights in round 2, right? In the iteration 2. Based upon that, we're going to run our weak learning algorithm again, and this time we get H2, right? We get H2, which is best classifier, but we still misclassified 3 negative examples, right? But now the error is not 0.3. It is reduced to 0.21. Why? Yes, exactly, right? Because those 3 negative examples were correctly classified by H1, right? So they were downweighted before the training in iteration 2, right? So now when we got H2 to classify those examples again, because their weights are decreased, so the error will be decreased to 0.21, right? And one might be curious, like, how do we calculate this error, right? Here is the general formula. So to calculate the error, we're going to account for the weights for every training example. We subtract by half. We subtract half by minus half, and then summation over every training example. For each summand is just the weight multiplied is by I, h of xi. H of xi is a prediction. Right? How to understand this formula? We consider 2 cases. First, if your prediction is wrong, meaning that your y is 1, then your prediction is minus 1. Or in opposite way, your y is minus 1, right? The true label is minus 1, but your prediction is positive 1, right? So you can see in both cases, your product is simply minus 1, right? Which indicates you actually misclassify this example. Right? On the other hand, if your prediction is correct, right, the product is always 1. Either both your prediction and the ground truth label are positive, which are 1, right? Or both are negative, and 2 negatives that is 1 positive. So you can see that if you make correct prediction, you'll get your this summon will be just becomes the weight, right? Weight of the training example. If you make wrong prediction, this summon has negative weight example. And we can show that this arrow, this formula is essentially the summation of the weights for all the examples that are misclassified by the learned hypothesis. And regarding why, I would suggest you to show that by yourself. And it's a good way to better understand this definition and the proof. You need to leverage the fact that the summation of all the weights will be 1, and then everything is clear. Okay.
But how would you assign a weight?
Yeah, that's a very good question. Actually, we're going to discuss later.
Okay.
Yeah, but now let us just assume we kind of have a mechanism to update those weights. So now we finished round 2, right? And we proceed to round 3 or iteration 3. And before we train our weak learner algorithm again, right? We're going to update the weights of training examples again, right? So those 3 misclassified examples, of course, their weights need to be upgraded, right? And for all the remaining examples, their weights need to be decreased. So, and suppose after those updating procedure, those are the new weights. And based upon those weighted set, this newly updated weighted set of training examples, we run our weak learner again. Right? We got our H3. Right? And now H3 is just the horizontal line. Right? And again, we have we still have 3 misclassified examples. Right? But because of those weighting procedure and you calculated the weighted error, you got error 3 is 0.1. Okay, any questions so far regarding these steps? Okay. Y is not 0.3 because more confusing error will weight the example again by this weight, right? So suppose now we stop here. We run our boosting algorithm for data boosting algorithm for 3 iterations. We end up with 3 weak learners, H1, H2, and H3. And how do we combine them to get the final hypothesis? Data boost uses a very simple strategy. We do a linear combination of those hypotheses. So we're going to assign a vote for each of those hypotheses, alpha 1, alpha 2, and alpha 3. Then our prediction, final prediction, will be the voted prediction, summation of voted prediction made by H1, H2, H3. And those votes are alpha 1, alpha 2, and alpha 3. So, for example, if H1, both H1 and H2 gives a positive prediction, right? Then the vote will be alpha 1 plus alpha 2. Right? But for H3, you give a negative prediction. The vote for negative prediction is alpha 3. And then to determine the final prediction, you just compare alpha 1 plus alpha 2 with after 3, right? Which one is bigger? You end up with which prediction. Okay. So here is the outline of the boosting algorithm. This is pretty general, right? This actually fits nearly all kinds of boosting algorithms. So we're supposed to be given a training set x1, y1 to xm, ym, right? The instances are labeled with either -1 or +1, right? And then we're gonna set a maximum number of training iterations, big T, or number of runs, right? Inside each iteration, we're gonna first construct a set of sample weights, dt, over this m training examples. We need to ensure that the summation of those sample weights are 1, right? Is 1, right? And then based on those weighted training examples, we find a weight hypothesis ht, and to have a small weighted error, epsilon t. And then we go to the next step, and then update the sample weights, and upon which we train another weight hypothesis and get a weighted error. And finally, once we finish all the big T iterations, we construct a final hypothesis which combines all the weight hypotheses together in a linear way. Now we need to specify what does it mean for construct a set of sample weights. How do we update the sample weights, right? And then once we have obtained the weight classifiers, how do we assemble them? Namely, how do we assign alpha 1, alpha 2, those values? So here's the rule for boosting, data boosting. Remember, the strategy to update the weights of training example is that according to the performance of the classification results made by the learner of weight classifiers in the last iteration, right? So if that example, a particular example, was misclassified by the classifier in the last iteration, then we're going to amplify its importance, right? We're going to increase its weight. And the example has already been correctly classified. Right? It's not that important. We should downweight. We should decrease the weight. Right? And how can we implement that? Right? So initially, as we mentioned, we're going to use a uniform distribution over all examples, meaning that we have the same weight across all examples, which is 1 over m, right? But after T runs, right? Suppose we have already had dt, right? The weights of the training examples in the last iteration, right? And we got hypothesis h of t, right? That was learned in iteration t, right? And we also got an error, epsilon t, the weighted error of epsilon t, learned on the training, performed on the training set. And now we'll proceed to t plus 1 run. Right? We want to find a hypothesis so that examples were incorrect, incorrect classified by ht, we're gonna increase the weight. Otherwise, we can decrease the weight. And here's the rule of data boosting. So for a particular example I, if ht, the classifier learned in the last iteration, right, correctly classifies the example I, right? We need to downweight its importance. How can we do that? We multiply the previous weight by e to the power minus alpha t. So alpha t is a non-negative number. So again, e to the power minus alpha t is less than 1, right? So actually multiply with a factor less than 1. So you actually decrease the weight, right? If you make a wrong prediction, the last the classifier, the weight classifier in the last iteration make a wrong prediction for this particular example, right? We need to increase the weight. How do we increase the weight? We multiply the previous weight of this example by a factor of e to the power of alpha t. This one is bigger than 1, right? So actually increase the weight. And finally, you're gonna normalize those updated weights to ensure their summation is 1, right? How do you normalize? You just just multiply dti for each example I by the corresponding factor, right? And now you add them together, you got your ZT, your normalization factor. So again, we can merge these two rules together in one formula, right? By the observation that this product indicates if your correctly predicted or not, right? If the prediction is correct, and then this product is always 1, meaning that you're performing downweighting, right? Otherwise, it's actually 1. You actually promote the importance of the example, right? Any questions so far?
I'm unclear about the ZT value. What is that?
ZT is just normalization. So meaning that, okay, I need to ensure that after the updates, the summation of all the examples, their weights are 1, right?
Oh,
If you simply multiply DTI with the corresponding factors, their summations are not guaranteed to be 1, right? So you need to normalize it. You need how to normalize that? Okay, first you just multiply the weight of each example by the corresponding factors, right? And now it just adds up those updated weights. We got ZT, right? And then you divide each individual weight by the normalization factor. You can ensure this their summation will be 1.
okay.
Any other question? Okay, great. So this is our rule, right? So there is one remaining question. How do we identify alpha? What is the alpha t value? So alpha t is determined by the weighted error epsilon t, meaning the training error after the training error of the learned classifier in the last iteration, epsilon t. As we mentioned, they are just the summation of the weights of all the misclassified examples. So you calculate alpha t as half logarithm 1 over epsilon t or epsilon t, right? So remember, no matter how weak this classifier is better than a random classifier, meaning that epsilon t should be less than half, right? If it is bigger than half, then that's horrible, right? It's even worse than just random guess label, right? So the error is less than half, so you can show that alpha t will be bigger than 0, right? 1 over epsilon t over epsilon t will be bigger than 1, so the logarithm will be bigger than 0. So we got alpha t. Now we plug them into those formula to get updates of all the weights. And this alpha t are also used to vote the prediction of each weight classifier in the final stage. So eventually, the classifier HD will get a vote of alpha t in the final classifier. So those alphas are the same thing as we just listed, right? So now we're able to fulfill the details of these 2 steps in a more general framework, which ends up with our data boost algorithm, right? So now, if we take a closer look at the final state, okay? So after running our data boost for t runs, we'll end up with big T weight classifiers H1 to H50, right? And also we got big T values of alpha t, right? Remember, alpha t is computed according to the weighted error in the training set, epsilon t, right? So now we can define our final hypothesis. The prediction is a sign of the summation of alpha t times HTX. Why is this reasonable? Why is this reasonable? Any thought?
So each of them will either be plus or minus 1 because they're each voting positive or negative. And then the ones that have the bigger alphas will get more votes than the ones with smaller ones, and then the sign of all of that will just be the most votes.
Yeah, exactly. I just want to repeat what you said, right? So remember, RT is just a vote, right? And the prediction made by each weight classifier is either 1 or minus 1, right? So actually, do this summation, you're actually computing the votes for the positive prediction and votes for the negative prediction, right? And if the final result turned out to be positive, meaning that, okay, the total votes for the positive prediction is bigger than the total votes for the negative prediction, right? So then your final prediction will be positive, right? Otherwise, if it is negative, it just means, okay, your negative prediction, the votes is bigger, right? And then you end up with a negative prediction. And here is the full average. So given training set, have training examples, and each training instance is labeled as either -1 or +1, right? Initially, we're gonna set an equal weight for each training example, right? And then you just run big T iterations and find a classifier. In each iteration, you find a classifier whose weighted classification error is better than chance, meaning that your epsilon T should be less than half, right? Otherwise, your RPT value will be negative. That's not acceptable, right? So you compute this vote RPT, 1 minus epsilon T over epsilon T, and then you also use those votes to update the weights of the training examples. Right? Then you finish this particular iteration, and then you move to the next iteration and train a new classifier based on the newly weighted training examples. And do this again until you finish all the big T iterations, and finally you end up with a big T weight classifiers, right? Then you use this rule to make the final prediction. So I believe this algorithm framework is clear enough for everyone to implement your own AWS algorithm. Okay? And the learning of this, we didn't specify the details for to run the weight learning algorithm because it really depends on which particular weight learner you choose. For example, in our homework, you're going to use decision star. Right? You only train a decision tree with one level, with one or depth being 1. Right? But then you can fit them into this whole framework. Right? So the final look, right? If you look back to the toy example, right? We know that we've got 3 weight classifiers, 2 verticals, 1 horizontals, right? If you draw the decision boundaries, you see those can perfectly separate all the positive and negative examples, and the decision boundary is nonlinear. It's quite complicated, much complicated than each of these individual weight classifiers, right? That actually showcases the power of the boosting algorithm. Okay, let's continue our discussion on Thursday. Thank you.